Okay, so we were just looking at the formal definition of a limit and using the delta epsilon proofs to do that. But we really aren't going to be doing that when we're showing limits exist or don't exist. So we're going to jump into the next section, which is going to kind of review what a limit is. But this time, we're really, in particular, only worried about one-sided limits. Because sometimes we saw that limits don't exist, that one side of the graph coming in on the left was not the same value as we came in on the right. But it's also important to be able to kind of recognize what's going on with the graph when you're approaching that value. So just looking at one side can tell us what's happening and will help us to graph these. So let's just kind of review a notation. So remember, for a limit to exist, that the limit as x approaches c, and we would denote from the left with that little negative sign in the exponent of f of x, is equal to L. Let's say the limit as x approaches c from the right of f of x is equal to some value m. We said in order for a limit to exist, that the limit as we approach on the left also has to equal the limit as we approach that value on the right. So in order for a limit to exist, we want to show the limit as x approaches c on the left of f of x equals the limit as x approaches c on the right. So in this case, L would have to equal the same value of m. Well, you might have, let's look at a couple different equations. And so I normally don't use the same examples the book is using when they're trying to spell out the section, because I think that, oh, well, if a student wants to really go back and read the section, then they have more problems they can look at. But I think this one is a great example, and we'll be dealing with absolute values in a function. And so first of all, let's recall what it means to be an absolute value of a number. So let's say we had our function f of x is equal to the absolute value of x. Well, there's two different possibilities that can occur, right? You can either be plugging in a positive number for x, or you can be plugging in a negative number for x. We know that when we plug in a positive number for x, that it's going to give us back the same value that we had plugged in when we were taking the absolute value of that. Where if we plugged in a negative number for the absolute value of x, the value we actually get back is the negative of the number that we have plugged in here. So we can technically rewrite this as what is called a piecewise function. And so it really depends on the value of x. We're going to set the domain separately for each piece. And so if x is less than or equal to 0, actually, let's say just less than 0. If x is less than 0 here, so if I plug in -1 in here, the y value I get back is really the negative of that -1. So it's going to be negative x. So the absolute value of -2, if I plug in a -2 into this equation, that tells me to use this piece because it's less than 0. -2 is less than 0. Negative of -2 equals +2. If you decide to put in your input and that number is greater than or equal to 0, that same value that you plugged into the absolute value is what the value you're going to get back as your output, which is just x. Okay, so in this case, and you might recall that if you looked at the graph of that, f of x, that would just be a v. So I can see right there, I could take the limit anywhere and I would get the same value back as if I had plugged in that number wherever I saw that x in that limit. So for instance, if I wanted to look at the limit as x is approaching 3, well, if we look at this, let's look at what f of 3 is. Well, look at, is x less than 0? Is 3 less than 0? Is 3 greater than or equal to 0? Well, 3 is bigger than 0. So that would equal to 3, or the absolute value of 3 is 3. Okay, so anywhere you chose that c value, you would get back either c or negative c, but that limit would exist. But let's say we have a different function. Let's say we have the function g of x, and g of x is equal to the absolute value of x all over x. And we want to look at the limit as x approaches 0. Shouldn't have written it all out because I could technically do my notation. And so if I look at the limit as x approaches 0 of the absolute value of x all over x. So first thing you guys want to do when you're looking at limits as x approaches a value, just first see if you can plug it in and get a result back. If you can, then great, and we're good. If not, when we get some indeterminate form, like we saw 0 over 0 or infinity over infinity, we have to go in and we got to manipulate it. And so first thing, and there was limit rules, and so that we could look at the limit if you had a rational function. This was the same thing as the limit as x goes to 0 of the numerator, absolute value of x, all over the limit as x goes to 0 of x. Well, if I plug in and go in and plug in 0 wherever I see an x in my, what I'm taking the limit of, I get the absolute value of 0 all over 0. Well, absolute value of 0, 0, 0 over 0. This is an indeterminate form. This is where the knowledge about knowing about absolute values and looking at them with as a piecewise function is helpful, because there's really two separate values that we can get back. So let's first think about this as, let's come in on the right-hand side. Actually, let's do the left-hand side, left to right. So x comes to 0 as we're coming in on the left of the absolute value of x all over x. So let's kind of think about this logically. If we are plugging in a number close to 0, but it's on the left of 0, we know that that number is a negative number. And so if we're going to be plugging in a negative number, so a negative number close to 0, all over, and the absolute value of that, and this is the same negative number close to 0. Well, if you take the absolute value of that negative number close to 0, it's just the opposite of that, which is the positive. So it's going to be this, so this is going to be a positive number. close to 0, all over the negative of the number close to 0. Okay, so let's say maybe that value is a. So that would have been the absolute value of negative a all over positive a. And this is, sorry, absolute value of negative a over negative a, which is a over negative a, which is negative 1. Doesn't matter, any value you plug in there, you're going to get this negative 1 if you're on the left of x equals 0. So if I plugged in negative 1, which is not so close to 0, but the absolute value of negative 1 is 1 over negative 1 is negative 1. 1 over negative 1 is negative 1. So it's a horizontal line here. What's going to happen though, I'm not sure, and then it's an open circle, right? We can say that it's undefined. We can't have 0 in the denominator, so we know it's undefined when x equals 0. So same sort of kind of reasoning if we're approaching it on the right. This time though, when we're getting closer and closer to 0 on the right, if we take the absolute value of a positive number, it's still that same number all over that number. So this time though, the limit as x approaches 0 from the right, the absolute value of x all over x, this is equal to the positive over the positive, let's say of a, which is just equal to positive 1. Undefined there, but any number that you chose that was on the right, that x value, is going to be a horizontal line there. So because the left and the right hand limits don't equal each other, we know that the limit as x approaches 0 doesn't exist. Of absolute value of x over x. Oops, wrong place. Doesn't exist. Knowing and talking about what's going on the left-hand side and what's going on the right-hand side helps us to see what's going on just in general with the graph. And so sometimes talking about left-hand side limits and right-hand side limits is helpful. The other thing that could happen is maybe you're looking at a function that the domain is limited. It's not infinite. So for instance, maybe we had a function f of x equal to the square root of x. If we talk about this function is only defined, the domain is only values where x is greater than or equal to 0. So the domain of f of x. So domain are all the inputs that you can plug into your function for your variable that will spit back a real number. If I plug in numbers that are negative underneath this radical, it gets me back an imaginary number, which is not real. So the domain of f of x, one way I can write this is x has to be greater than or equal to 0. Sometimes they want it in interval notation, so from 0 to infinity. Sometimes they want it in set builder notation, so let me just do it real quick. So you have that set notation, you have the variable you're talking about, in this case it's x, you have a vertical line, and I'm going to state that x has to be greater than or equal to 0. This vertical line here, this reads as such that. So this says the set of x such that x has to be greater than or equal to 0. But those are three different ways you can express the same thing. And so if we went and we graph this function, which hopefully you know how, or you should know how to graph, you're going to have this kind of halfway parabola. And so notice that the domain here, right, you don't have any piece of the graph that is left or less than 0. And so in this case, really the left-hand side and the right-hand side technically don't exist because it's not part of the domain. And so just thinking of this as, well, let's then just look at the limit here as x approaches 0 from the right, right? Because that is part of the graph of f of x in this case, we're getting back 0. Okay, so there's a couple functions that we got to be careful of. And these are a couple trigonometric functions, and we're going to look more at the proof of why this exists later in the class when I get to show you L'Hopital's rule that will help us prove it in a nice, easy manner. But for now, I'm just going to kind of show you, and we're going to just kind of hopefully you agree with me that these limits are as they are. Maybe another thing to think about is, remember when you were graphing trigonometric functions? So when you graphed your function of sine of x or sine of some argument of x, unless you had some number in front of that sign, or as long as you didn't add something else or subtract something else, your range was between -1 and 1. So whatever number you plugged in for the sign of that, sign of something had to fall between -1 and 1. And so if we look at some f of x, let's say is equal to sine of 1 over x. Thing is that, okay, again, I know that when I look at this is pretty much all defined except for can't have 0 in the denominator. So sine of something undefined is undefined, but we want to know it's okay for something to be undefined, but a limit exists. So we want to know, does a limit exist here? So note here, you have a restriction, x cannot be 0. F of x is undefined there. Okay. Any other limit, we could just go in there and we can plug in that value for x. If we're looking at x going to any number except for 0, that's what we're looking at or want to know what's happening. So the limit as x goes to 0 of sine of 1 over x. Recall, we actually, I believe, looked at the limit as x approached 0 of 1 over x. If you plug in numbers, and if you look at this graph of 1 over x, it looks similar to this. One over a number that is less than 1, that's positive. 1 over 1/10 gives us 10. 1 over a 100th gives us 100. 1 over 1,000 gives us 1,000. And so this is going to be growing to infinity if we're coming in on the right, but the left, 1 over a negative number close to 0 is giving us going to negative infinity. And so either direction, this is going to be coming and getting growing really fast, really quick as we get closer and closer to 0 on the right. And same idea over here. And so what's happening is you're starting to plug in numbers that are getting really close. And they're going to be bouncing back and forth, oscillating back and forth really, really quick when you're taking that sine value in between here, but it's oscillating between the -1 and 1 value. And so any number you plug in, you can't say it's getting close to that value because, or close to 0 because of that oscillation. And I'm not sure if I graph this and we can try it. Let's see what happens on Desmos when we graph that. Oops, that's not what I meant. I want a new tab, new window. Okay, so I'm wanting to look at y equals sine of 1 divided by x. And notice, like I said, there's going to be an oscillation here, and it doesn't matter how much I zoom, it's just going back and forth so fast. And so it's not approaching one number as we get into the left or the right of that. Okay, and so because of that oscillation, we would say that the limit doesn't exist. We're now, and I'll go back and write that in a second, but we also, and since I have Desmos open right now, we're also going to be looking at something that is going to help us to know, what if the function was sine of x, all divided by just the same argument we had, x here. And I wanted to look at the limit here as x approaches 0. So notice it's actually undefined because we can't have 0 in the denominator, can't have something that sets the denominator equals 0. And if I go in here and I click on it, if I get close enough, it will say undefined. When x is 0, it's undefined. But notice, right, as you're coming in on the left, you're getting a value of 1. And as x is approaching 0 on the right, the y value is getting closer and closer to 1. And so that limit approaches 1. Okay, so we're actually going to even manipulate this a little more. So let's say this was sine of some coefficient times x. So let's say 5. Notice if we also put this over 5, we get 1. So if this sign of the argument we're taking, this number is the same in the denominator, any value we do there, so if I plug in -10, and I plug in -10 here, we're still getting the limit is approaching that argument, or 1 here. And so we're going to use algebra or math to help us manipulate things so that we can find a limit if it's almost in this form. And we'll talk about that in a sec. Okay, so just coming back to the note piece, we saw that this is undefined. Does not exist. The graph oscillates really fast. Between -1 and 1, or y equals -1 and 1. Therefore, let's to talk to you guys about that. Triangle made with the dots is another way to write therefore. The limit doesn't exist. Okay, but then we also looked at the limit as x approaches 0, a little bit different form, sine of, and I'm just going to do it generically, a of x all over a of x is equal to 1. And this comes from the theorem. And this theorem says the limit as theta approaches 0 of sine of theta all over theta is equal to 1. Okay, I know you guys really want me to prove this to you right now, and we can probably do that. You would actually do that with using the sandwich theorem, but we're going to actually jump in and actually be able to look at some limits using this fact, or these facts right here. And so let me show you how you would do it. And I just want to zoom in so my pen is nice and big, or fatter. Let's see. Okay, well, let's just do a generic one. So let's say you have a limit as x is approaching 0 of sine of k times t. This will kind of show you how you can do it for any problem, all over t. Oops. Sorry, this shouldn't be x go to 0. It's actually t, or a variable t, not x. And it tells you that k is a constant. So technically, if I can manipulate this denominator to look like the same argument here, kt, then I would know the limit. And so what we have to do is kind of manipulate this so we can multiply this by a fancy 1. So let's say, and I want this denominator to look like k times t. So let's just multiply this by k over k. So let me just kind of rewrite this. So this is the same thing as a limit as t approaches 0 of k times sine of kt all over k times t. Same value, same argument. And the thing is that we have this k here. Well, k, remember, is just a constant. And with the limit rules, we said that that's the same thing as pulling the constant out front and taking the limit as t approaches 0 of this sine of kt all over kt. That approaches 0. So by the theorem, this is 1, and we have k times 1, which is k. So what about the limit as x approaches 0 of tangent of 2x over x? Okay, so looking at this, we should be able to tell this is undefined. Well, it's multiple places it's undefined, but it's undefined here when x equals 0. But we can go in and see what happens. Let me just rewrite this. Sorry, it's been a couple months since I've taught trig. Tangent of 2x, this is same thing, right, as sine over cosine. So sine of 2x all over cosine of 2x. So notice that this piece, if we're looking at the limit as x is approaching 0 of just sine of 2x over 2x, I was actually just trying to figure out where it was undefined. If it was undefined at 0, it's not. And I plug in 0 here. Well, this gives me sine of 2 times 0 all over cosine of 2 times 0. Well, this is sine of 0, which is 0, all over cosine of 0, which is 1. So it's okay to have 0 in the denominator and a number not 0 in, 0 in the numerator and a number not 0 in the denominator. And this is equal to 0. So I just want to show that it was undefined where we're taking the limit because of this x in the denominator. And if we went back in and we plugged in 0 wherever we saw an x, I got the tangent of 2 times 0, which we just showed was 0, all over 0. So this is 0 over 0, which is an indeterminate form. So we got to go back and manipulate. So instead of writing like this, let's rewrite it in terms of sine and cosine. So we have the limit as x approaches 0 of, well, this is the same thing as sine of 2x over cosine of 2x times x. Doesn't matter what side the x is on in the denominator. Let's break it down. We can break this down as a multiplication of 2 fractions and be equivalent. So if I wrote this as limit as x approaches 0, well, I'm trying to manipulate this to use that theorem, sine of something constant times x is the same thing over the constant times x. So let's write it as 1 over cosine of 2x all times sine of 2x over x so this piece, that second fraction, almost looks like it that we can break it down and make this 1. Well, we need this denominator to have a 2. And so again, we can multiply by a fancy 1 to make a 2 down there where we want it. And so if we multiply this piece by 2 over 2. So I'm just going to rewrite it equivalent. Instead, I'm going to move this 2 right here that I'm multiplying in the numerator to be with the first fraction. So I could write it as 2 all over cosine of 2x times sine of 2x all over 2x. And so using limit laws, remember limit law said if we look at the limit of a product of two functions, we can break it down as a limit of the first function times the limit of the second function. And so we have the limit here as x approaches 0 of this 2 all over cosine of 2x times the limit as x approaches 0 of sine of 2x over 2x. We know this piece because of our theorem, this is going to 1. Let's go back in and plug in 0 wherever we see an x in this other limit. So this would be 2 times the cosine of 2 times 0 all times what this limit was. And we just saw that that limit was times 1. And so we have 2 cosine of 0 is 1. So we have 2 over 1 times 1. So with manipulation, that limit when we were first looking at it was in indeterminate form, didn't tell us anything, but we found that the limit of that function goes to 2 as x approaches 0. So let's look at that real quick with a graph. So we had tan of 2x all over x. So if we're looking at the graph as x is getting closer and closer to 0, so notice that it's approaching our y value of 2. On the left and on the right, again, we said it was undefined there, and if we find it, there should be an open circle. And that point should say undefined if you got to click on it. Somewhere. Yeah, there you go, open circle. But the limit exists. So there's one other one that we will hopefully be able to recognize and find the limit. Actually, maybe not. Maybe that's the next section. Maybe go over one more. Okay, let's see if we can get through one more example. Or not. It's gonna just go slow. So maybe we should just wait till tomorrow and go over another example similar to this. And then we'll just finish off on this. And then we get into what I think is pretty good and kind of ties in together limits is continuity in the formal definition or mathematically what it means to be continuous at some function x.